welcome to the ASV's March AstroTalk. Tonight we'll be treated to Science Fact double feature presentation. So 2 presentations for the admission fee of 1, even though it was free to get in. Talk 1 will be presented by Emma Barnett from the Victorian Space Science Education Centre on the topic of the state of astronomy education and outreach in Victoria. Following Emma's talk, we will hear from Dr. Richard Miles, who will be discussing the explosive history of Centaur Comet 29P. And following tonight's presentation, we will have supper here. If you're watching online, sorry you miss out. And should the skies be clear, we will have the observatory telescopes open for viewing, and Emma is also going to access the VSSEC radio observatory for those who are in attendance who might want to see how they use their radio observatory. Now, before we begin, in the spirit of reconciliation, the Astronomical Society of Victoria acknowledges the traditional custodians of country throughout Australia and their connections to the land, sea and community. We pay our respect to the elders past and present and extend that respect to all Aboriginal and Torres Strait Islander peoples today. Now, talk 1, the state of astronomy education and outreach in Victoria. Having worked within astronomy education and outreach for 10 years, Emma is very passionate about bringing astronomy to students across Victoria. Her job at VSSEC currently involves visiting regional and rural schools to provide astronomy resources to those that are often disadvantaged by their distance from Melbourne. In this AstroTalk, Emma will discuss the current trends and issues in astronomy education, in particular in Victoria, and what organisations like the ASV can do. Emma, the floor is yours.
Thank you. All right. Now, I know you've just done an acknowledgement of country, but I would like to as well. I begin today by acknowledging the Wurundjeri people of the Kulin Nation, traditional custodians of the land on which we gather, and pay my respects to their elders past and present. And I extend that respect to Aboriginal and Torres Strait Islander peoples here today. Now, this is actually quite important to me as my master's, if you're unaware, is on Indigenous astronomy education, and I'm always trying to work with Indigenous people as much as I can. Now, to start this talk, I want to see some hands in the room because I'm going to aim particular topics, particular concepts, depending on who's here. So, it's hard to see. Can you raise your hand if you are a teacher or work in the education field in any way? A couple. Okay, can you raise your hand if you work as a scientist or an astronomer or anything like that outside of ASV? A couple, awesome. Can you raise your hand if within ASV you take part in any kind of outreach or education? Yeah, much more hands there. Fantastic. All right, I know who I'm aiming this all for. So to start off, I'd like to tell you a little bit about my background and how I came to the role I'm in today, so you understand where these ideas are coming from. All right, a lot of the opinions in this talk are mostly my own, from observations I've had over my career in astronomy and education, but I'll let you know a little bit about that first. So I'm originally from Deniliquin in rural New South Wales, and I went to the University of Melbourne to study physics. While there, I started doing tutoring and things like that, but I also started volunteering with telescopes in schools with Claire Kenyon, who many of you know. That was sort of my starting point of getting into astronomy. And in postgrad, I was actually working on gravitational wave data analysis. I didn't love it, but I did a lot of outreach while doing that, including uni tutoring and lab demonstrating as well. And I ended up leaving that study to go work both at Swinburne and the University of Melbourne. So at Swinburne, I had a role as the Astro 3D Education and Outreach Officer, which meant I was their outreach person for Victoria for Astro 3D, which is a centre of excellence in astronomy. And I also worked at the University of Melbourne at the same time, 2 jobs, as basically a TA for the first year physics subjects, including the first year astronomy. I'm still doing that now, very part-time. So I was working on developing a lot of the content with the lecturers, trying to tweak the material that we're teaching, and that's ongoing as of today. So after COVID, in those roles, I got a job at VSSEC, and I've gone back to study part-time. So to let you know a little bit about VSSEC, anyone here been, hands raised again, anyone here been to VSSEC in person? Only a few. Good. All right, VSSEC's pretty new, not many people have, but I'd love to actually have a chat about whether we can get you guys into VSSEC in person at some point. Hands up if you've heard of VSSEC, you know what it actually is. Only a few. Great. Okay. So VSEC is not a uni or anything like that. It's one of 6 science and maths specialist education centres across Victoria, and it's located at Strathmore Secondary College campus in Strathmore, near Essendon, right in the middle there. Through a focus on space science, VSEC encourages students to participate in science, technology, engineering and mathematics. And we also allow teachers to use the science of teaching to teach science. All right, so what that means is that VSEC staff and the advisory board are made up of both teachers and scientists and government people. Our educators, the people running the everyday programs, are often university students studying science or teaching. And a lot of our programs are scenario-based. So our students, primary, secondary, are sent into a program in a role and they're fully immersed in what they're doing. So we're using a lot of tools, huge variety of things to teach space science, to teach science skills from all years F to 10, and then also some VCE as well. So there's over 20 programs there, both on site as well as outreach. A big one is the Mission to Mars program, where kids are put in the whole suits. They go out onto our little surface that we have at the centre of VSEC there, and they work with mission control to make their way through a mission. But there's a lot of other programs there as well. So the 2 that I am coordinating are 2 newer programs. They are funded by the Challenge and Enrichment series. Right? So these are government-funded programs, and these 2 are only exclusively for government schools in Victoria. If you're not eligible for that, we have many, many other programs. But this is where I've been working with a lot of teachers around Victoria. So our radio astronomy program is quite new. It only started being put together in 2020. We have a 3-metre dish, a 3.1 metre dish, I think, outside Tallarook in the middle of Victoria there. It's the only radio telescope in the world that we know of that is exclusively for high school students. So no researchers, the general public don't get to access this. It's just school students. You might get a little glimpse tonight, but we'll see how we go. So that program is run remotely. So we provide all of the material for the teachers, and the teachers in their classroom access our telescope without us there. There's a lot of trust and a lot of training in this program, but that's basically how it's been run. And last year alone, this reached 2,742 students around Victoria. So that's how many used that telescope just last year. Now the STEM Academy, this is the one that's sending me around Victoria to actually work with teachers directly. So we got a grant to give 30 telescopes to schools around Victoria. They're pretty decent telescopes, three grand each, a good bit of kit. And so I was travelling to regional and rural schools from Mildura down to Malakuta and every direction in between. And I was running astronomy nights. I was training the students on the telescopes, that's one there, and how to use them. There's photography as well. And then we added lots of other material that we could do during the day, like the classic water rockets, which is quite fun. So this program, last year we reached 6,916 students in a year. All right, so between these 2 programs in 1 year, I almost hit 10,000 students, 9,600. In that, I got a lot of time speaking with teachers, with the students, and a fair few of these schools I've actually gone back to run either one program or the other, secondary astronomy nights, and building that rapport. So I started to notice a lot of trends in what's happening out there in our education and outreach programs, as well as all the other ones that I've been part of over the years in my various other roles. So what I think of our education outreach programs, organisations, everything that's out there, I could try to categorise them into 3 different types. We have our research-based organisations, so things like our ARC Centres of Excellence, CSIRO, anything like that. We have our more education-based, so that's something like VSEC, perhaps ScienceWorks, lots of other smaller programs that are especially education-based in Victoria as well. And then we have our more public interest ones. So this can include what ASV does and a lot of the other societies around Victoria, as well as online content, spaghettification even, all that sort of stuff can be qualified into that grouping. Now, no one's locked into any one particular thing. Of course, say ScienceWorks is education-based, but they're open to the public. Of course, that's there as well. But this is just a matter of thinking of where the funding's coming from, who's putting the time and effort into it. It comes from different areas, and they all have different reasons for what they're doing. So while looking at it in that way, I've sort of started noticing particular trends, problematic trends, yes, but also some aspiring trends. Now, aspiring, I don't mean inspiring, I mean, what are the teachers wanting? All right, so I'm going to focus particularly here on the schools. If you did listen to the recent Studification podcast that I did, I spoke a little bit about how there's a lot of outreach out there and things like that, but a lot of public events, we're getting those same people every time, and to try to reach other people, we've got to get them in the classroom. And to do that, we've got to actually figure out what's going on. So, a big problematic trend that's getting worse this year, especially around regional and rural Victoria, teacher shortages and their time. All right, if there are teachers in the room, you're probably quite familiar with this. But basically, there is a couple of new rules about how teachers can take time in lieu. And if you're trying to run an astronomy night, teachers can't get there. So the event can't run. This is a major issue I'm facing with my astronomy nights at schools. As well as that, there are huge shortages both in teachers and CRTs. All right, so casual relief teachers. Now, for example, just last Friday, I was at a school in regional Victoria, I won't name the one, and we were there to run our water rockets all day, years 9 and 10. In the afternoon, the room that we're in, we were sort of booked out for the day, and of course there were normal classes in there that had to get moved. And when the teacher came to the room to run her normal class, she saw us in there and just broke down crying. So clearly, she's had a horrendous week. We almost got cancelled because there was no single teacher available until the principal was suddenly available because their appointments cleared up, so we could have the principal in the room as the teacher observing. There was no available teachers. That teacher was crying because she'd been thrown around school all the time. Everyone was filling in. They had to actually combine a couple of Year 7 classes that afternoon because a teacher was away and there was no one to fill. All right, so this is a huge issue that we're facing. Anytime you're trying to run something in a school, you have to consider what your program, your outreach, whatever it might be, how that's going to affect the teachers. Now, on the flip side of that, looking at what teachers are wanting, they really, really want something that's prepackaged. All right, so whether that's content for in the classroom and you just give it to them and go, here are your lesson plans and activities, have fun, or whether that's equipment that's been designed to be easy to use. So, for example, the telescopes we gave out, it was very, very hard to get 30 schools to actually take on that program because the teachers were terrified of the amount of equipment that they'd have to learn and didn't have time for. But the smaller things that we're doing, like the water rockets, we're giving them the kit and saying, have fun, here's your lesson plans, here's how to do it from years 3 to 10. They're loving it. All right, so anything that is easy to engage with and prepackaged, ready to go, schools are loving that. And they want more of that. Now, something that's becoming more common post-COVID, I think, is a bit of student disinterest in a lot of fascinating things like astronomy. Of course, there's always people in the room that love it. They're always there. But from the general population, I think so many people are getting so much new information all the time. There's so many cool new activities. There's 3D printers in most of the schools I visit now. There's so much interesting stuff out there that when you turn up with a telescope, they go, okay, sure. So it's something that we're actually having to overcome to think about how we advertise these things to the schools. Now, a way to do that and a way that teachers are loving this is thinking about what's happening right now. What's happening in astronomy, what's happening in the news. There are a lot of things that you guys are quite familiar with. So if we can relate to what we're doing to anything that's happening in the news right now, the teachers are taking it on. The students are taking it on a lot more. This is something we have to focus on a lot. Sort of as I mentioned before with the time, but teacher training for equipment and content. If you're running a telescope night of some sort that you're expecting teachers to be taking part in or helping run with a telescope or anything like that, it can get very, very difficult to do. This also came into our radio astronomy program. We are giving this program to schools to run in their classroom without us. A lot of them were worried about the amount of time and the amount of learning for this. So what I ended up doing was saying, hey, I'm going to have a less than 1 hour Q&A with all the teachers booked on for this term. I'm going to show you in 15 minutes how to use the telescope. You'll see it's not that scary and you can ask any questions you might need. So just taking that time to try to help them out could engage a lot more. I've got multiple bookings from those teachers, but that's been a massive hurdle to overcome from teachers wanting to take part, but they just can't overcome the amount of training that they're worried they need because they don't have the time for it. Or the emotional effort is the other side. Now, on the flip side of that, a lot of schools are thriving any kind of new technology, new tools, telescopes especially, but anything new and exciting, they're loving it. If you can find a way of relating your material to equipment schools have got, like the 3D printers I just mentioned, fantastic, they'll take it on. So if there's any way you can tweak yours to be new and exciting, they'll take it on. A common problem, especially with general public events, is that you're always preaching to the converted. It's hard to run an astronomy event and tell everyone why astronomy is so exciting because everyone in the room is going, yeah, I agree. Very, very difficult. So something you're trying to do here is to reach those students that might have lost their curiosity, that we can try to re-spark it, some that have never really thought about astronomy that much, and trying to find them, hunt them down. It's very, very difficult. But on the flip side, something that's actually popping up quite a lot now is the Indigenous astronomy and introducing that into our curriculum. As of this year, it's being introduced into the VSSEC curriculum. And so there's a lot of new resources that the teachers are just willing to grab the second they can, especially if it's coming in a prepackaged form. All right, so these are the trends that I'm noticing as I'm visiting these schools all around rural Victoria. I do see some of it in our metro schools as well. These aren't just isolated trends, but if you're doing any kind of astronomy in regional or rural Victoria, these are huge things to overcome, or huge trends to utilise. So sort of asking what can we do as ASV, as many organisations out there, we really need to look at combining our new technology, making it accessible. That also means if it's a remote access in any way, you've got to make it accessible and available to the teachers as simple as possible, and give it a unique selling point. I'm going to go into that in a little bit more detail shortly. So we can look at, say, telescopes. Everyone here loves a telescope. We're trying to get telescopes out to as many schools as we can. There are already a few organisations doing that. So I've mentioned telescopes in schools. That's been around for a fair few years, and it has had a bit of a dip with COVID, but they've actually employed someone new this year, or end of last year, to change it, revamp it, and bring it back up. So you're going to be hearing more about telescopes in schools soon. So they've been loaning telescopes to schools around mostly Metro Victoria, but some regional as well, and running astronomy nights and things like that. Astro 3D, who I used to work for, and I was part of this program, they have a program called STARS, Scientists Taking Astronomy to Regional Schools. They too are giving away free telescopes to schools all around Australia. All right, simple, easy to use telescopes, sure, but they're giving it around all around Australia. Any school that could have applied during their expression of interest period is getting one. And our program, of course, where we're running around Victoria trying to give these telescopes away. All right, so there's already a lot of schools that have access to telescopes. I would love there to be more, yes, but there is an issue here, is that a lot of these schools that have got equipment already don't have the knowledge behind it. Whether that's they're too far away to visit often for astronomy nights to provide that knowledge or anything like that, or it was part of a program like this one where it's a one visit kind of thing, and then good luck, here's some resources you can use. But this is where I can see someone like ASV jumping in. So these schools have got a lot of the resources already but can't use them. You guys have got the knowledge. This is something that could be done. There are other things out there that some of the bigger Centre of Excellences are doing. So Ozgrav, you might be familiar with, they've got their classic VR headsets they take to all the schools all the time. Astro 3D are actually like 2 years into their VR headset development as well. So this is something that these bigger university-based programs are doing. And Dark Matter, their new program is called the Network Schools Program, which is a lot like our STEM Academy program, where they're going to be developing a network with a bunch of schools around the state. And I know a lot of people here are very keen on developing a network with schools. So there's like 3 of us already doing something very, very similar. Whether it's we try to avoid too much overlap with the same schools or we work together, that's something we can think about. But a big thing here is thinking about those unique selling points of all of these. So Ozgrav is focusing not on light, but on gravitational waves. It's something a little bit different. The Dark Matter Centre as well, their education outreach programs are being developed right now, and you will see them appearing in schools very, very soon. So if you know anything about dark matter or any way to work with these kind of equipment, see if you can get in contact with them and a way to reach out with them. Otherwise, standard telescopes, there are so many out there, but we don't know what to do with them. On the flip side, there's also a lot of remote access telescopes. So Pulse at Parkes, the Parkes telescope itself, has a program that schools can book and they can operate the telescope for a short period of time. We have our own one called the Radio Telescope Program that you guys might get a bit of a preview with later this evening. ICRA over in Western Australia. Currently, it's only really available to WA students, but it's something very, very similar as well. All of these are remote access free radio telescopes. They all have their own program. Everything's already developed, but they're all a little bit different. So Pulse is something that's a high quality research telescope. You only get it for a short amount of time. There's limited bookings. Ours is a bit less quality, but it's free whenever a school might need it because it's only schools that can book it, which is why it's free tonight. ICRA's one, it's a really like high-tech one, but it's only for WA. So if anyone else is interested in kind of remote access telescopes that are ideally free, there's models out there that we can already base these on. And a lot of teams like this have got all their materials online to use. Now this is just radio telescopes. There's also a lot of remote access optical telescopes out there, like iTelescope and things like that. So there's so much out there that already exists that we could base a lot of things on. Something else that we should really be doing that a lot of organisations are trying to do is relate their material, their program, their event, especially public events, to the things happening in the news. And so one of the big ones, hopefully someone can tell me what this is immediately. Yeah, good, okay. James Webb Telescope. So a lot of public events are running, amazing things about James Webb Telescope, and it's a great public talk, and then they bring in anything else they can. All right, so they're combining these events. So it's not just an astronomy night or something like that, but pushing it all together. All right, so James Webb's a classic one that you can introduce in some way. But another one that I'm not seeing much of yet, but we will be seeing more and more over the next few years, is the Artemis missions. All right, so the Artemis missions, we're trying to go back to the moon. We've got an amazing rocket, we're going to be exploring it. Yes, it might be more STEM-based, but it's still related to astronomy. So something we can consider is how can we do Artemis-based missions not at night? Can we do something with our telescopes? Can we do something in the classroom during the day, looking at the moon when it's up in the day that's related to Mission Artemis, that's going to get people excited? Is there something there? Is there an opportunity there? All right, so this is just one idea that we could be doing, but this is what I'm sort of trying to get you thinking about is how can we combine our outreach, our education programs with big events like Mission Artemis, or perhaps even combine it with local things like if you're trying to visit a school and run an astronomy night, why not find out when their parent-teacher night is, because the teachers will already be there and paid their time in lieu. You can probably get in that way. Just something different. All right? There's going to be a teacher observing, there's kids running around. It's just a different way to think about your event. All right, so even things like running teacher professional development conferences, anything like that where you're not running a standard nighttime astronomy night, because that's where a lot of our issues are at the moment. All right, so what I'm trying to go through here are, it's going to load, some of our different problems that we're facing. We've got that there are many telescopes out there available to students. I'd love it if there were more, but who knows how that'll go. That even with your public astronomy nights, ones that the schools have already got access to or own, but there's a lot of knowledge that's not being passed on to these teachers. So this is something that I think ASV and a lot of other organisations can really hone in on. How can we provide that knowledge knowing they've already got most of the tools? There are a lot of limits on teacher availability for school programs, especially at night, but they also need packaged material. We need to develop programs, we need to work with teachers and scientists, put these things together and give it to them in a way where we go, here's your 1 hour lesson, have fun, rather than trying to organise a huge, massive event. But this also comes to, say, incursions and excursions. They really want excursions that can tick off particular curriculum points that happen during the day, easy to do. All right, something to carefully think about. There's a need for a lot more daytime astronomy in schools. All right, radio astronomy is one way to do that. But if we can think about using sunspots, which are getting better at the moment, what side of the peak we're on, I think we're still on the slightly getting better, but we're at a great time for sunspot activity. Those optical telescopes that a lot of these schools have can be used in that way if we can find a way to do that. All right, so that's just one way of doing daytime astronomy. The moon, Venus during the day, whatever it might be, or just other small hands-on activities as well. There's lots of opportunities to build on these big events and combining with other groups, collaborations. So you need to have a really careful think about what it is you're actually wanting, who you're trying to reach, what target audience, primary schools, secondary schools, general public, whatever it might be, and see who's already in that area. So that you're not competing against anyone, you're working together, trying to find a way through it. Now, what I've said through here, none of it's a big answer to the question, what should we as ASV do for outreach and education? Absolutely not. I can't tell you that answer. I don't have that. But I'm just trying to give you an idea of what trends I'm seeing, and hopefully the people that are very interested in this have already got ideas in their mind of little things they could be doing, whether it's with ASV, whether it's their own private work, whether it's something else, whatever. That's what I'm trying to be here for. So I'm going to start a bit of a Q&A. So if anyone's got questions or even an idea that they just want to share with the group about something that's popped up in their head while I've been talking, now's the time to ask them. Anyone in the audience
Stunned
feeling
silence.
powerful?
Any questions? No hands? Oh,
here we go.
I knew it would happen.
I'll go first because then a rush will start. Well, yeah, idea popped in my head while you were talking that we do how to use your telescope for members. So is that an idea we could maybe do for schools? We have the knowledge if you have telescopes. Yeah, we can help.
Yep.
Yeah.
Yep. Whether that's an online package that's like pre-filled, whether that's someone that's reaching out to you directly, that sounds absolutely perfect. That's the sort of thing that you could be sharing that knowledge for. Fantastic.
Yep. Question?
I've come over from England, and the UK is similar in the sense that there's lots of schools out there, and the problem is that you have to get someone to go along to the school to help, with knowledge. So we've got a lot of societies, 230 in England alone. So if we take the ASV, is it possible to sort of match up the members of the ASV and their locations with the schools who are interested? Or are there things preventing that, like data protection? Yeah. Because, I've been involved in the Forks Telescope project, and, it's part of the problem is that people keeping others away from the schools. You can't, I've got a friend who's goes around with a planetarium. He's done tens of thousands, and he goes to school and he gives the class, and then he expects to be able to drive out, but the school gate's locked because the rule is it's locked. So there's a lot of things working against it. Any comments on all of that?
Yeah, absolutely. So, for example, our STEM Academy is now, STEM Academy program, it's a network of schools. So we've got 30-ish at the moment, and I'm going back to them throughout the year, which means if there's a way to align where your members are and my schools, I could be that point of call to help do that. I don't have enough time to organise huge events or anything, but I can certainly be the point of contact between the two. So I could be the one to reach out to the teachers that I'm working with directly to say, hey, we've got these members in your area, this is what they can offer, what do you want me to help with? All right, so same with the dark matter particle physics one, they're trying to create a network as well. It might be slightly different, but you could do the same thing there to say, these are the services we could offer, you just be the point of call. So I'm absolutely happy to be a connection between ASV and the other various societies out there around Victoria, and where my schools are that I'm visiting, perfectly happy to be that reference point. Yeah.
Wonderful. Any other questions? Oh,
Down the back?
down the back.
Oops. Yes, while after I retired, I was tutoring at Monash University, and we ended up arranging for bus loads of students from Monash University to go to our dark sky site at Heathcote, and we showed them things in the sky that they'd been studying at the university, and that worked out quite well.
There is a lot more flexibility in the university curriculum for things like that. So as I sort of mentioned, I'm still working for Uni Melbourne right now, and just last week, a different university reached out about our labs that we developed for first year astronomy and whether they can completely take our labs and use them for their course, provided they write Uni Melbourne on it. Absolutely, we're sharing that content around, but that means right now, in the next 3 weeks, 4 weeks, I'm helping the lecturer plan the first year Uni Melbourne astronomy course for next semester and what we're going to do for the labs, all that sort of stuff. And there's very much opportunity there and flexibility and things like that. So often we try to run an astronomy night at uni is often being the best way to do it because they're uni students and there's about 400 of them. But there's certainly a lot of flexibility there with all of the different universities around Victoria that we could be reaching out to. Definitely. Yeah.
Another question?
It's not really a question.
Yeah.
We do have actually a member in the radio astronomy section who is a physics teacher for high schools.
Mm-hmm.
And he's been working on a project for 6 months now whereby the students are to be able to build a radio horn with a SDR.
I think I know who you're talking about, yes.
That'd be Paul.
Paul? Yep.
Okay, so
Yes.
you do know all about it. So we're probably displaying some of that work at the next Messier Star Party.
Yeah, well, something like that is actually what I had a school reaching out to me, a Geelong school, about 3 weeks ago, saying, we want to build our own backyard radio telescope. How could we do that? And I was just buzzing to say, I could almost directly give you the material. I know someone that's doing that. So if you guys, this idea in particular, but anything else like that comes to mind of an activity you can do, if you don't think ASV has got the way to pass it on, if you want to help develop that material, that equipment, whatever it might be, I could perhaps present that further along and share that idea under the ASV name, of course, but I can be that point of call. So I'm very, very keen to see how that radio horn goes and how technical it might be. I'm very excited about that, actually, yes.
I did say you get bombarded with questions. There's more.
Thanks. I recently had a wonderful trip overseas, and I went to a couple of planetariums, and one of them I went back to because I was so impressed by the engagement of the leader, and secondly, the kids were so young. I'm like middle of primary school. And I looked at the minimum age they recommended for some of the sessions, and one of them was 5 years and up. Kids know a lot, but my question is, it's not really at a mathematical or at a higher level. Naturally, there's a progression through schooling, and I wonder whether there are units that use chemistry and physics at year 11 and 12. In Victoria, because I'm unfamiliar with the current curricula. I've been out of touch for quite a few years.
So in the VCE, physics in particular, there's they're sort of developing these ideas called options. So the school can pick a couple, ideally the students pick a couple and they all run at the same time and the students get to choose what they do. And there's a lot of astronomy in there, which means we could be reaching the students that are really, really keen and want to do astronomy as an option, but there's not as much in the full curriculum anymore. There's a lot of things like relativity and things like that, but at year 11, year 12, it's the elective ones that we're really hitting. So for example, our radio telescope program is open to those year 11 students wanting to do that as an option. But yeah, it's slowly, unfortunately, being removed from the curriculum in terms of core content in that way. There's a lot of it in like 7 to 10, absolutely, year 7 to 10, but not at that year 11, year 12 level. Different, bit difficult to think about. Yep.
Hello, I'm Andrew. I'm a teacher, and I've been teaching astronomy in the school for 4 years or something like that. I'm actually employed as an astronomer for a school.
Oh, awesome.
So we need to talk later.
Yep,
but
sounds good.
My experience is that daytime astronomy is the key to engaging students. That you've got to have students studying astronomy during class, during the day. And that means for the work that we've been doing, it's been things like iTelescope, it's been using networks, using telescopes overseas on the other side of the world so that you can actually do astronomy during the day. So we need to talk some more.
Yes, I definitely recommend iTelescope. We use it at uni. It can be a bit expensive though, so for some schools it can be quite a problem, but there are a lot of opportunities out there to use optical astronomy elsewhere in the world, so you can get to do that during the day, and I definitely recommend it for any school that can do that. Yeah.
Do we have any more questions? Oh, another one?
I'm absolutely happy to chat later as well, don't worry.
Might take a couple more. There is a couple more and then we'll get our next presenter up.
Hi, my name's Kerry. I missed the first 10 minutes, but what I wanted to ask you was, I know quite a number of teachers that would be interested in this program, and even my youngest, when she heard that I was coming tonight, she's like, oh, please, can I come? And I said, no, it's not for kids.
Yeah.
But I'm going to reach out to the school's principal and let them know about what's available. But if they are interested, who do they write to? Or I missed that.
Yeah, so the two programs that I'm doing specifically, the radio and the VSSEC STEM, they're only for government schools.
Yep.
Because that's what the grant is covering.
Okay.
But if they're a government school, absolutely reach out to me directly or jump on our website. If you fill out the booking form, it'll come to me.
Sure.
If you're non-government, a lot of our other programs are 100% available to you, just not these particular two.
Okay.
That's
all
all.
right. Okay. All right.
Yeah.
Thank you.
Any other questions? No? I think we've exhausted them all.
Fantastic.
Emma, thank you very much.
Thank you. I'm very happy to have chats with you all later about any ideas that are running through your head, because I could see a lot of people just going, oh, actually, and I'm very happy to chat to you all later about that. So thank you very much.
So what was that? Oh, yes.
I've
Can we
got,
want to pop them
I've
back?
also got
You got cards?
cards I can hand out later.
So hopefully we've
see
stirred
if this
everyone's mind up. That was probably the main
Let's get
reason I
back
wanted
to-
to get Emma along, is because there's a lot of opportunity out there for the ASV to get involved in many different areas, whether it's radio astronomy, solar astronomy, visual astronomy, remote telescope work.
There you go. Take a
there we
photo quickly if you need.
Take a picture, it lasts longer. So, yes, thank you very much for coming along tonight. It was a great talk, and I'm sure they will chew your ears off and you'll get a lot of emails. I know Chris, our junior section director, has already
A couple
reached out
people
to
have
you.
already reached out to me. And
Oh,
it's been
a
a
couple- okay, there
hectic
you
start
go.
of the year that I haven't got to you
There we go.
yet, so I want to chat in person if we can.
So if you have reached out, she has got your email. She's not ignoring you. Now, we'll move on to
Yeah, thank you. Thanks, everyone.
a round of applause, yes. Sorry. I'm in presentation mode. I totally forgot about the round of applause. So thanks for reminding me, audience. Now, our second speaker
Yep.
is going to talk on the explosive history of Centaur Comet 29P. Dr. Richard Miles. His first astronomical recollection was in the summer of 1957. He's only 21 though. Having seen the brilliant white band of the Milky Way in the non-light polluted skies on his way home from holiday. He became Assistant Director of the Asteroids and Remote Planets section starting in 1984 and Director in 2005. Oh, I can hear me on the... I was getting feedback from Stuart's phone. And Director in 2005 and serving as the British Astronomical Association President from 2005 to 2007. We have royalty among us here, people. Dr. Richard mainly studied asteroids and comets, all of which are examples of small solar system bodies, and has a special interest in outbursting comets, starting with 17P Holmes in 2007 and 29P SW1 in 2010. I went a bit fast. We are getting there. We're nearly there. We have a slide up. Dr. Richard, welcome aboard.
Is that?
That works.
Hi there. Is the sound working?
Yep, sounds
Yeah,
working.
okay.
Floor is yours.
Yeah, well, thanks for having me. And the main reason I'm over from the UK is this mob here. Every year, except in COVID, I come along and visit and meet the granddaughters. But for this second talk, we're going to try and show how amateurs can push back the frontiers of science. And there's one particular object out there in our solar system that's been rather under-researched by the professionals. For understandable reasons, you have to keep looking at it, and amateurs are ideally placed to do that. It's explosive, partly because this is what this object does. It has these cryo-eruptions, around about 20 a year. And And it's also explosive because professional astronomy hasn't come to terms with this object. The theory of comets cannot explain how this behaves. And so what I'm going to show you this evening is some of the findings that amateurs have made possible by observing this. And it is the most observed comet we have. Okay. So I'll just quickly go through the history in terms of when it was discovered and some of the professional involvement. So in 1927, it was having what we call an outburst, where the brightness suddenly increases by maybe a factor of 10 or 50. And it was discovered by Arnold Schwarzman and Arno Wachmann. So it's unfortunately got this terrible name. It's not called Comet Halley, it's called Comet Schwarzman-Wachmann. But it's numbered as 29P now. And ever since it was discovered, it's continued to have these outbursts. And Pat Römer, working at the US Naval Observatory, was one of the main observers photographically in the 50s, 60s, and 70s, trying to map out what this thing does. But the most well-known comet astronomer of the last century is a chap called Fred Whipple. And he really, he's had 7 honorary degrees. He's discovered 6 comets. And the strange thing is, he graduated from UCLA in California in 1927, same year that the comet was discovered. And his first paper that he published was actually on comet, what we call 29P. And his last paper, serious paper, was also on that 53 years later. These are the 2 papers. The first one is he's trying to understand the orbit of it. And the last paper was to look back on all of the history by 1980 to try to explain what it is that this thing's doing, what's it like. And he made a stab of it, but he was a long way short of it. Fred was he actually coined the term icy conglomerates in 1951 or so in a paper, and the press switched that to call them dirty snowballs, conveniently. But now we actually understand them more as icy dirt balls because there's more dirt and dust in there than water ice. Okay, now why is this subject strange? Well, the traditional comet is in an elliptical orbit with the sun near the center of gravity of the orbit, and each comet usually shows a tail as it approaches the sun and it's warmed up. But one of the key points about this Centaur comet, it's not a Jupiter family comet, is its position in the solar system. It sits just beyond the orbit of Jupiter. It's around about 6 AU from the sun, and it's in an almost circular orbit. It got there by coming from the Kuiper belt, maybe 1 or 2 million years ago, and the major planets, the gravity of Neptune, Uranus, so gradually pulled it in towards the sun, but it's got trapped by the gravity of Jupiter and Saturn. It's in that region of space, and for the moment, it's probably been there for many, many thousands of years, and this is partly why it's unusual. There are other centaurs, and centaurs do show activity. But here's a montage of images, which shows what happens, what you see. To begin with, it's just almost like a point of light, and then there's an explosion, effectively, on the surface. And this material is projected out into space, which is a vacuum, so it keeps traveling out further and further away, and you get the outburst coma expanding. So Damien Peach put together that montage. Right. Now, that's the sort of history and puts it into perspective. Amateurs are really ideally place to observe this. And my main ulterior reason for wanting to talk to you and to have it recorded online is to appeal to observers in the southern hemisphere to pursue this comet over the coming years. The last couple of years, it's been at a very high declination, and so it's not really been accessible from, say, New Zealand and Australia. But starting this autumn, it's moving south, and it'll be moving down to about 22 degrees north declination. And then thereafter, it will just get further and further south and end up in Sagittarius. So later this year is an ideal time for us to gear up the southern hemisphere observers and obviously use telescopes like in Chile and so on to try to follow this object on a 24/7 basis. The key, the reason why the amateurs have been successful is that typically we'll observe it maybe 3 or 4 times a day through the 24 hours from different longitudes on the Earth. And we're able to see the point in time when an eruption takes place. And I'll tell you more about that later in the talk. And we can time the eruptions to a median timing accuracy of about 4 hours. And that's one of the things that you as an amateur or even a school, if you mobilize schools to observe as well, they only need to take one image to be able to get a measurement of the brightness, and that gives you a data point on the plot. So it's a very time effective object to observe. You don't have to sit there for ages. And okay, now I'll show you what it's been doing since about the last 8 years. And I'll show you basically, because it's out just beyond Jupiter, it's visible every year. And it's visible for about 11 months, in fact. So we've got the records of what's happened in the last 8 years. And I'll just run through the sort of thing. I'll explain, there's 3 what we call apparitions there, 2014, 15, and 16. And what we're plotting is the magnitude, but it's a reduced magnitude so that it normalizes it. So if it didn't change in brightness, it would just be a straight line, okay? And it'd just be, say, like an asteroid. But as you can see, it shows these peaks. But if you look at the axis here, this is about 7 magnitudes, which is about over a factor of 600. So these eruptions are causing an increase in brightness of a factor of 100. That's a strong outburst. And prior to 2014, strong outbursts were all that was seen. But in 2014, we discovered that this object has what we term mini outbursts. And you can see them here. And if we go on to 2017 to 2019, you can see that qualitatively, they're not the same each year. If we go back, you see that middle one there shows very few mini outbursts and very strong outbursts. Whereas down here, there's very few strong outbursts, just a couple here. Moving on, 2020, this is just ordinary magnitude plotted now. And one of the things that I did is I published a couple of papers in the professional literature based on data up to 2014. So it was all the minor planet center data and so on. And I identified a 57-day periodicity in these strong outbursts. And here we are in 2020. You can see this repeated. Sometimes it's maybe 57 days, sometimes it's twice that. And then if we move on to 2020, So what you can do is you can observe the objects once there's been an outburst. So if as an amateur you discover an outburst, we have an observing campaign that's been running now for some years, you flag it. What happens then is we get access to large telescopes to try to study what's going on. And the Fawkes telescopes, the 2-meter telescopes, are the preeminent tool for doing this. And this next set of images are just processed images taken with a 2 meter, and they've been processed so they show the detail of what's happening close to the nucleus. Takes away the spherical light from the coma. And what I'm showing here are 3 pairs, and these are strong outbursts. First one was separated by 58 days, and 56 days, and 56 days. And if you look at this is maybe 20 arcseconds square, it's very much the close-up, you'll see the similarity. So one of the hypotheses is that the nucleus of the comet takes 57 days to spin once. And what you're seeing is an eruption from a vent that then re-erupts one rotation later. So that's the hypothesis we work on. And that was put out, as I say, I published in 2016. And since that time, we've been observing it particularly carefully. In 2021, in September, it had its strongest outburst on record for several decades. And what happened in September of 2021, it had 4 consecutive outbursts, each about a day apart. And on the basis of that, the Hubble Space Telescope was scheduled to observe it some weeks later. The day before it was due to observe, it went into a failure mode. It shut down. Sod's law, isn't it? It's usually the clouds up here, but Hubble doesn't have that problem. I thought we'd lost the observations, but what happened was that it was still on the program, and it took a month to get Hubble back working, and it actually took the images around here. And it actually caught this outburst here. There's an outburst here. And now I'll show you the last one. It's a good example. The latest apparition, it's still going on, is this one. So here we are. It's in March now. We've just reached the end of that graph. And one thing you'll see is that each outburst is very sudden. We rarely get data on the rise, which means that it only takes an hour or 2 to rise. I'll show you how we've managed to actually follow a rise. But when we look at the 57-day period, we can look back at all the outbursts that we've detected over the years, and we can see whether the 57-day period is maintained, whether we got additional evidence for it. So this is 20 years worth of outbursts, and what it is it's been expressed as the intensity of the outburst. Those are the sort of 0.6 up to 300. The units you don't need to worry about, but they are effectively one unit is one area of the nucleus, the bare nucleus without any coma. So if it's 100, the coma is 100 times brighter than the nucleus. Okay, and what this shows is that there's a seasonal variation, and that there are times, this is a rotational phase, so we assume it's a 57.65 day period, and you see this pattern emerge. Now, the new data from the amateurs, starts here, and we discovered these mini outbursts, which are shown in red, and before that date, they weren't known. And you can see that this enormous expanse of what's called rotational phase space is devoid of strong outbursts. So that confirms that the 57-day period must be right, that was predicted on the basis of data up to this point. And so I'm reasonably confident that this object does rotate very slowly. I'll skip on. One of the things that you look at in any object like the Earth, they're normally spinning on a tilted axis. So the Earth's 23 degrees creates the seasons. Well, every other object that's tilted will also have seasons as it goes around the sun. Now this comet takes nearly 15 years to orbit the sun. And so what I'm plotted here is I've added up the intensity of the outbursts each apparition and normalized it so I'm comparing like with like. And you can see there's a repetition, and this is really seasonal activity. So the main peak will be probably summer in one of the hemispheres, say the northern summer, and then the second peak is the summer in the southern hemisphere, and it's the tilt that creates that. Right, I said it's difficult to catch an outburst actually happening. This was our first, by chance, successful one. It was on this particular date, and you can see the data plotted, but I'll show you, just by chance, 9 observatories were observing it at roughly the same time, and this is what the light curve looks like. So there's some professionals at the Trappist Observatory and quite a few amateurs, and you can see what happened. The amplitude of this one was equivalent to 1.3 nucleus equivalents. But you see the general shape, see how quick it is. It takes about an hour to really get to 80%. But then we were really lucky the following year. One of my colleagues is a French observer called Jean-François Soulier, and he's actually set up a robotic telescope in Haute-Provence specifically just to observe this comet. So if the comet's above the horizon and it's clear, his telescope and it's dark, we'll be observing it. And it was this particular one that he managed to get. What he does, he takes an image every minute. And there have been 3 strong outbursts in 1 year, and he was lucky enough to catch the middle one. And this is him and his, it was an 8-inch telescope at the time. And I'm not sure, let me show you the video. Oops. Oh no, I don't know what it's doing. Just trying to, oh. What is it? There we are. Ah, I see, it's the HDMI. It doesn't like it. And, yeah. It's not going to show it, is it? Yeah. It's not showing what's on my screen. Oh well, we'll skip that. I'm trying to get a video to run this. Come on. I'm going to have to go out and go back in, I think. I'm going to do that. So I wanted to show you the video, which just shows that see if we can go from there. There we go. Okay. So anyway, the video would just show over an 8-hour period. He monitored for 8 hours. It would show it kicking off, and this is the light curve we got from that. So having that light curve, it's a very strong outburst. Enables us to start to try to fit theory, some sort of modelling of what's going on, and this hasn't been published yet, but I've put together some models to try to describe this. And when it first starts, you get a cloud of material that starts from one particular place on the nucleus, and the cloud is opaque. And as it expands, it reaches a point where the cloud starts to become translucent, what's called optically thin. And it gets thinner and thinner as the expansion goes on. But during the first 20 minutes or so, all of this, this rise here, the cloud is actually opaque. And it gets to about 20% of its maximum intensity, and it starts to get thin then. You can model it with a circular expansion and fit a model to the data, and you can plug in actual figures like the expansion speed and get a good fit. One of the indications is that the shape of that is caused by the fact that the outburst happens near the limb of the nucleus, near the edge where the sun has risen. So the nighttime finishes, and where the cryovolcano is, the sun shines on it, and within a day or two of it sunrise, you get an outburst. This is a plot of the Comet thinning. So on the left is the transmittance, and you can see that there's no transmittance at around about 20%. It doesn't quite get to 100% because the intensity doesn't quite reach what it should, because some of the ice volatilizes. This is the full light curve over 8 days. So you can see the sort of data that we've got. It's really, and you can fit models to the shape of this in the different phases and the expansion phase later on. Okay. I haven't mentioned how big this comet is. It's actually about the biggest periodic comet we know of. And we think it's about 60 kilometers across. So Halley, for example, is only about 15 kilometers on average. So one of the things about an object with 60 kilometers, it's got actually quite a significant gravity. So the material that gets thrown out is typically thrown out about 100 meters per second. But anything that's moving slower than the escape velocity will eventually fall back onto the nucleus. And because once we're signaled an outburst happened and we can get a 2-meter telescope onto it, we can start to actually study much closer into the nucleus. And the material that comes out is very black. It's typical of a dark asteroid or a dark meteorite, and it doesn't reflect a lot of light. So to an extent, after an outburst, you'd expect sort of material, a black rain to fall or something to fall back. But can we detect this? Actually, I haven't got time to look at both, but we look at the August the 22nd outburst. So you can, and if we study that by just looking at the 2-meter telescope photometry, what we do is we measure the brightness of the coma with different sizes of aperture. So effectively, we measure the brightness of the coma at so many thousand kilometers from the nucleus. Just go back. Yeah. So it's worth me explaining what this is. The magnitudes that you've seen before have only been using apertures around the coma, which is around about 20 or 25,000 kilometers in radius. This thing is 6 AU from us. It's much further than most comets that we study. And you need a larger telescope to be able to go closer in. And what you do is you measure the amount of light of different sizes as you go down, and you compare it to the stars in the field. So it allows you to get down to about 3,000 kilometers from the nucleus, the brightness, with reasonable accuracy. Now, this one here, this is the data as I worked out from the 2-meter. This is in August 2020. And I couldn't understand it, couldn't understand the there's been an outburst, and then you had this complicated pattern. So the very top curve is 1.5 days after the outburst, and you can see its magnitude is so brighter and got that shape. And then the next curve is 2.5 days, and see it's starting to fade. But between 2.5 days and 4.5 days, it drops down this first arrow in a 2-day to this point. And what that looks like is that a certain amount of the material that got thrown out has fallen back onto the nucleus, disappeared from the whole aperture. But I couldn't then understand, what's this? And I went back and looked at each of the photometry, and it turned out there were actually 2 outbursts, 36 hours apart. So if you just plot our traditional way of measuring it at 25,000 kilometer radius, we had this, I hadn't noticed that there was this second kick. So this second fall change is because after the second outburst, the second lot of material fell back. And look, after 7 days, they just superimposed. So it's extremely difficult to understand what's going on. It's almost as though there was an object that came out and it crashed back onto the nucleus. And it took a few days. So if something's projected out, it doesn't necessarily fall straight back. It misses it on the first orbit, second orbit. So maybe the material was a clump. So that's a discovery that's possible because of the amateur work. Finally, to finish off, how are we doing for time? Okay. I'll tell you a story about what's happened since December. But it starts 5 or 6 years ago when I was in Berlin. And I met a friend of mine called Mike Kretlow, a German amateur. And his forte is in working out orbits from the astrometry of objects and doing occultations, predicting when a solar system object is going to go in front of a star. And he and I were talking at it's a European Planetary Science Conference, and we quickly came to the conclusion that the astrometry of this object, 29P, must be wrong. We published a couple of papers in the Journal for Occultation Astronomy, and the reason it's likely to be wrong is that the outbursts move the center of light of what they measure, people are measuring, away from the true nucleus because of all this bright coma that's often there. And most of the observations are done right after an outburst. And we showed that it's likely to be, and there's 42,000 observations in the Minor Planet Center database in here. So what I did is, because I've been working on this for quite some years, I got all the data from the 2-meter telescopes. There's one in Siding Spring, Australia, one in Hawaii. And I came up with about 620 odd accurate measurements of the comet when there wasn't a strong coma, when it was, you could see the nucleus clearly. And I gave a poster presentation in Canada in October on this, and met the guy from the Jet Propulsion Lab who's responsible for the orbits, of comets. And he said, he said he agreed with me that, it needs to update it. So I sent him the data, the astrometry, and we use Astrometrica to measure the position accurate using Gaia positions and so on. I sent the astrometry to JPL and also to the Paris Observatory that also measure it. And Mike himself did the calculations. And we came up with the fact that if you use the MPC data, the position of where we think the comet is out by almost 1,400 kilometers. So the guy at JPL, Shantanu Naidu, he used our data and basically replaced the old MPC data with this new data, which covers almost one orbit of the sun of this comet. And this is the new orbit that he used. And when you compare it, when you compare where that is, these are the positions that the Miles-Kretlow orbit gave, and the one at the top there is the one, the MPC. Now, if you use the MPC positions, you never ever observe an occultation, because the object's only about 60 kilometers across, and you're 1,300, 1,400 kilometers away from where you should be. So people didn't know that, and even, so that was important. And another reason why Centaur needed to have a good orbit is that the James Webb Space Telescope. Remember, James Webb is used, it's only just being put up, but it's used for all the important targets. The telescope was scheduled to observe it in February, and it did. And it needed to know the accurate position because the field of view of the telescope is 3 arc-seconds square. Right. The results will be out in a year. And it had anyway, so on the basis of that, there was an occultation forecast to cross Southern California, North Mexico, and this is in December 19th. And basically, there were 5 occultations, and we were able to see the shape of the nucleus. So this is really, and the triangle in that is the position with the occultation added. So the prediction and the actual was within about 50 kilometers, maybe. And from now on, we know where we've proof of where this comet is. We know where its orbit is, accurate to 10 or 20 kilometers. And so we'll always know where to look, what stars to look for. And in fact, earlier this morning, there was an occultation visible from Europe, but I think it wasn't able to be observed because of the full moon. I've written an article which is in the current issue of the Astronomy Now magazine in the UK. It's a 6-page article, and it talks about how we've been successful in what I call chasing comet shadows, because the star occulted projects a shadow of the nucleus of the comet on the Earth. So like a total eclipse of the sun. So if you happen to be in the shadow path, you'll see the star disappear. There is, as I say, I'm based with the British Astronomical Association, and we've got a thing called Mission 29P. It's called that because back in 2019, 2 groups in the States tried to get NASA to send a space mission to visit the comet, and they were both turned down. So in the absence of a space mission, this is the next best thing. And occultations are a really good way of doing that, but also all the other stuff. There's one page on the website that gives all the news and so on of what's happening. And back in November, I also set up a mailing list for observers, really, that if you want to know what's going on or take part, you can sign up to the mailing list. And Bob's your uncle, as they say. Hopefully we'll make lots more new discoveries. And I do encourage Southern Hemisphere observers to pay particular attention to this particular object. Thank you.
Yeah. Do we have any questions for, straight away, Barry. How you going?
In an outburst, Richard, what percentage of the mass falls back? Is that possible to estimate that?
Yeah, a strong outburst is like maybe 1 million tons. But because it's 60 kilometers across, if you weigh an object that's 60 kilometers across, it's still very small. So we don't think its rotation rate is changing because of the outbursts. I think that's maybe, if there's a lot of mass, it's like a rocket sort of thruster, and it changes but this is such a big object that it's able to stay rotating at that speed. Remember, it doesn't get too close to the sun. It's always in a very stable environment, thermal environment. So yeah, but these are big events. You know, the strongest was the one in September 2020, and it was something like 400 or 500 times the area of the nucleus alone. So, you know, you're probably looking at 5 million tons mass of material. Okay.
Just a little bit. Any other questions? Yes, we've got a couple.
Thank you for that. Can you please explain the concept of an outburst and what impacts does it have on surrounding entities or planets or comets? And, you know, what causes the outburst?
Yeah, I was leaving that to be one of the questions. I'm glad you've asked it, because none of what I've said really is try to explain what's causing it, but I have published in the professional literature hypothesis. So to get these very sudden changes, you have to have a fissure that opens up, and you have to throw the material out very quickly. So from the shape of the curve, we know that it's only throwing material out for minutes, only a matter of minutes, and then it shuts down. Every outburst we see is a sudden one. There's no continual build-up or, you know, phasing out. The only way you can get that is if there's a crust. It doesn't necessarily have to cover the entire nucleus, but there's a crust, and that there is effectively there's a three-phase system, liquid, solid, and gas below the crust, and that there's a certain amount of pressure that the crust can hold before fissure. Now, the hypothesis is that the mini outbursts are more like geysers, and the strong outbursts are caused by more like a volcanic eruption. And the volcanic eruption, like Mount St. Helens, for example, it happens because there's a sudden release of gas deep within the volcano, because the pressure is taken off. When the volcano starts to erupt and the pressure is taken off, it's like a champagne cork being taken out of a bottle, and you get this solution of the gas from the liquid. It's dissolved in the liquid. In the case of the Earth, it's water dissolved in molten lava, surprisingly. It's such a pressure that it's in there. And in the case of this object, it's likely to be carbon monoxide and nitrogen dissolved in hydrocarbons. But you can get the same effect. Instead of it being at very high temperature, this is happening at about 70 Kelvin. And another strange thing about it is that if it becomes quiescent, it won't stay quiescent long before there's a mini outburst. And it's almost as though that it's like at some time, it's almost like clockwork, that every 10 days or 2 weeks, it's got to a certain level of brightness, and it has a mini outburst. And I think that's evidence of the fact that there's continual production of gas inside beneath the crust, that there's a sufficient amount of liquids, hydrocarbons, so on, and gas, that the gas is moving around inside, and it transports the heat of the sun through the body of the nucleus. So if you look at the calculations, you can't get heat being conducted through a solid sufficient to power all these outbursts. You know, it's just too much energy being released. So what happens is the sun's heat sublimates ices, and the gas diffuses around within, and it then dissolves in some liquid at some point in the nucleus. And what that means is the gas has moved the heat from the surface to deep within the nucleus. So there is a process. Once you agree that there is a crust that holds a certain amount of pressure, you then have if you look at the physical chemistry, you then have these other processes for moving heat around. And essentially, that's I think, a good explanation. And I don't think you can explain the eruptions without there being a crust that can hold a certain amount of pressure. I think that's critical. So that would have been part of the talk. But thanks for asking the question.
With another question up here.
Richard, you mentioned the occultation a little bit earlier, which betrayed the shape of the nucleus.
Yeah.
Would you be able to tell us whether it's more spherical or more potato shaped?
Yeah. These are fairly accurate, these chords. The oblateness has to be about less than about 0.2. So for a comet, it's pretty circular, but it's not perfectly spherical. So what that suggests is that it's not the entire, it's not the entire subsurface of that's in hydrostatic equilibrium. There isn't a liquid beneath the crust covering the entire thing, because otherwise it would be a sphere, right, under its own gravity. So it means that there are regions on the nucleus that are active. And actually the seasonal plot of the activity starts to give you some clues as to where it is, because it's only at certain bands, a bit like Jupiter, bands on Jupiter, the different regions, the thermal regimes are different. And the strong outbursts need to have a long period in the nighttime side to basically generate, to dissolve enough gas to start to create a strong outburst. And so it does support the fact that, it's not a binary like comet nucleus. It is pretty close to a sphere, but this suggests that it's not entirely, there are regions of activity and regions that aren't. Is that fair enough, Perry? Is it Perry? Oh, hi.
Do we have any other questions? Oh, another one? We'll have time for one or two more after this.
My question is, wouldn't the composition of the material that's found give us, obviously, clues of what gases are involved and, what gases needed to get together and cause the explosion?
Yeah. So we do know from the work that's been done from the ground that there's some emission lines when there's an outburst where you can detect carbon monoxide and also nitrogen. So we think those are the two main gases that are sort of powering this. Now the James Webb Telescope is going to open a new vista on the chemistry, because instead of just looking in the optical, it goes right out to 5 micron. And it also is going to map this 3 arcsecond square. It'll have the spectra for 900 positions in the 3 arcsecond square. So there'll be a map of the chemistry. And hopefully the James Webb the results that if they're successful will add, give an answer, a little bit more of an answer. Now, the James Webb observations were done during a period when the nucleus was nearly quiescent. Just over a day later, there was an outburst. but I think they wanted to observe it in quiescence. And one of the reasons they wanted to is that there is another way of measuring carbon monoxide from the Earth on this comet, and that is to use radio telescopes. So they looked at the radio emission lines for carbon monoxide, and surprisingly, they found that they're not really associated with the strong outbursts, that the CO, the carbon monoxide, seems to be there almost irrespective of the strong outbursts. So I think the explanation for that is that when, and I haven't got the data to show you here, but I've been working on it while I've been in Australia. But remember me saying how as it fades, it reaches a certain floor level, and if it reaches that floor level, it's going to outburst. But that floor level means there's still quite a lot of coma there. So what essentially is happening, if you were to get up close and personal to the nucleus, you'd see it fizzing away. You'd see gas escaping. You can't have a crust that's 100% sealing it. Any crust is going to have leaks and allow pores for gas to diffuse through. So the carbon monoxide in the coma is actually, if you add up the fact this is going on, day after day after day, whereas the outburst only happens for minutes. The material's released in minutes. If you tot up the amount of CO, most of it can come from it just fizzing out. And also those small mini outbursts. So the fact that James Webb observed it in this condition will be great, because it will test that hypothesis. It'll test the hypothesis of what's happening while it's quiescent. It never ever loses its coma. It will outburst rather than lose the last remnants of its coma, and that's because it's fizzing. The pressure's building up, and at some point, somewhere on the surface, and it's not all over. It's probably these regions, the sort of temperate regions. So the poles are relatively inert, and the equator gets just too much consistent. So it's these regions here, and the pressure it won't be able to fizz fast enough to release all of the gas that's being produced inside, and something has to give. So you get a fissure, and you get another mini outburst. So James Webb has observed it at the ideal time. I think it's much better to observe it in the steady state condition than to observe a real outburst, because real outbursts, there might not be that much gas associated with it, but by observing it at equilibrium, that is representative of the body as a whole, and that's what the James Webb data should show.
Okay, we have one last question.
Hello there. This is the third object that I know of, apart from Europa and Euclideus, that gives off geysers. I know scientists particularly look into those objects, those moons, especially with geysers, to see if there's formation of amino acids for life. Do you think it's something that could be possible on this comet? Is it something you're looking into?
The chemistry on the comet? The chemistry on the comet's interesting because one paper I wrote looked at the different chemical species that can be behind all of this. And if you look at it, you find that chemistry, Mother Nature has endowed chemical molecules with belonging to two groups, either hydrophilic or hydrophobic. So if you look at most chemicals that exist in the environment, they're either water-loving, water-soluble, miscible with water, or they're oil-soluble. Even the vitamins in our body. And for this object, because it's so cold out there, it has to be the hydrophobic chemistry that has to operate. So that's hydrocarbons, carbon monoxide, nitrogen, oxygen actually as well. The other class that's relevant to comets is, as I say, the water soluble. So that's water ice, carbon dioxide, ammonia, hydrogen sulfide, methanol, alcohols. So when we look at comets, we have to look for two different environments. And Jupiter family comets are coming close to the sun, are all operating in the hydrophilic phase with all those amino acids and so on, water soluble. And that's because the temperature is high enough, for those things to form liquids and gases. But when we go out to 6 AU from the sun, all of that material freezes, is solid and can't participate. But what can are those hydrocarbons that form. And the strange thing is that if you look at the chemistry of hydrocarbons, when you get these sort of gas forming and then liquids forming, with hydrocarbons they tend to coagulate or collect in one area. So how in the Earth, the oil that is discovered is very much, it's pulled together, and it's over the eons that the Earth existed, it's concentrated in certain areas, and because this comet has been in this present orbit for a very long time, it's quite likely that that you get liquids in certain areas, and that's where all the activity is. But it does have to be hydrocarbon based with carbon monoxide, nitrogen, and oxygen as the active, what are called hypervolatiles. Does that answer the question? Well, I didn't quite catch the beginning of it. What?
Oh, I just mentioned is it possible for
and is it possible for an amino acid to exist? Okay, well, remember I just said that if you've got water-soluble hydrophilic type chemicals, that's where amino acids will form. And it is, it's possible for them to form so long as you get liquids. I think that's the general thing. And, why I call this talk explosive is controversial. The idea of Fred Hoyle, they put together this idea that life came to the Earth in comets, in small objects where, as they get to the point where any part of beneath the surface starts to form a liquid, that's when you get the chemical reactions happening. And the cosmic rays and the energy, from a star, but mainly from cosmic rays, provide energy to promote the reactions. And so while these bodies are traveling between the stars, provided you can get liquid, this is the key thing. And it's a shame that professionals have avoided coming to terms with the fact that for many years, they always said you can't have liquids in comets. But I think 29P, it proves that there must be. And there's just one other piece of chemistry I should mention is that hydrocarbons, they're also called, alkanes are called paraffins. We all know what paraffin is. And paraffin, also you have paraffin wax. Well, if you cool hydrocarbons like methane and ethane down to the solid, they're identical to paraffin wax. So if in this comet, the basic liquid phase is hydrocarbons, when that freezes, it will be like a wax sealant. But if you take propane, just take that one molecule of propane, the pressure you need to hold the propane at to get it to melt is 100 millionth of an atmosphere pressure. You don't need hardly any pressure for propane to exist as a liquid. And what happens is the methane and the ethane dissolve in it. And you end up with a mixture, butane. And so you end up with this mixture. And it can exist at quite a low pressure, but it can still exist as a liquid. But if you get gas like CO dissolving in it, and nitrogen, that's when you've got to hold the crust, you've got to hold the pressure, and then the gas will keep dissolving in it. And it will dissolve in it to 100%, it's what's called infinitely miscible. And remember I said oxygen? Oxygen is oil-loving. Oxygen wants to dissolve in hydrocarbons and so on. Fish that have evolved in the oceans require oxygen to survive. But oxygen is an extremely poor, water is an extremely poor solvent for oxygen. So Mother Nature's managed, even with such a poor amount of oxygen present dissolved in water, the fish through their gills can use it. But oxygen and water don't really mix. Oxygen is a very poor, it's very poor gas. If you want CO2, you can get a lot more CO2. If you want ammonia, you can get, again, it's miscible in all proportions, ammonia in water. So oxygen belongs in a way in these cold objects like comets, and the new analysis of the Halley data, Comet Halley, they finally realized from the 67P work that Halley also was giving off oxygen, and that oxygen is actually quite a common constituent, but it's quite difficult to detect. Whether James Webb will detect it, we'll see. But it's, the chemistry of it is fascinating, and amino acids definitely will be present. And I think some of the primitive meteorites, they can detect some of them there. Yeah.
There we go. Thank you very much. Thank you, Richard, for a wonderful talk. Very interesting and engaging. Thank you, everybody, for coming along tonight. And give a round of applause to them. So I'll take the opportunity to thank both of our guests for coming along tonight and giving two wonderful presentations. Hopefully both of those have caused some inspiration amongst the crowd and those watching at home.
Don't forget to observe 29P over the next coming year.
There you go. So, there's a job for our members to go and do. Just also wanted to let you know there are still some tickets available for the Messier Star Party. We're expecting over 300 people to attend at the moment, so large bumper crowd. We have another new event, Wine Under the Stars. Shiraz Republic have come to us and asked if they could do another Wine Under the Stars. So that event's on our website as well. And we have our Easter raffle going, which also links to the tickets on the website. That's a Red Cat 51 and an Ioptron Skyguider. I was looking at Bill to make sure I say it right, with a tripod. Wonderful prize. So you can get tickets available for that. That's drawn on the 10th of April. Thank you, everyone, for coming along tonight. For those that are here, we'll get supper ready. And if the skies are clear, we'll go and have a look through telescopes, and hopefully Emma can get the radio dish going for us. And for those watching at home, thank you very much for joining us, and we look forward to seeing you at our next stream next month.